We will improve more and more. Yeah.
And Alessio Metti is a
Alessio,
colleague from
no,
ISMN.
Ah, sì. Sì. Possono mettersi seduti fra loro perché gerarchie delle cose.
Did you work
Poi
with Marcus?
parlare in inglese, cioè,
The same laboratory, no?
poi alla fine il capo delegazione,
Now he's retired.
He's retired for quite a long time, but he's still there as well.
Because I remember I met him
al limite
2 years ago.
Yes.
10 years, but
Still worked in occasion, so
No, no. Sì, ho visto che parlava con il cinese. Era impressionante, la gente di lingua.
but as Patrick tells me, we can start. We can start. Just 1 minute. Patrick, mi senti? Patrick, mi senti, Patrick?
Yes, I can hear you, Roberto. You can go.
Can we start? Thank you. So, you everybody for being here. I just wrote few lines to introduce Frédéric. It is my great pleasure to introduce Frédéric. Frédéric and I first met during my PhD. He was a postdoc on the same beamline, the SU3 beamline EDU. And since then, I've invited him several times. And only now he had the courage to face the Roman heat, let's say. So better than ever, anyway. Since 2004, Frédéric has been associate professor at the Chimie Physique ParisTech, at Chimie ParisTech at the PSL University in Paris. Today, he leads a laboratory combining STM and XPS dedicated to surface science and catalysis, with his research focusing on surface reactivity and nanometric and atomic scale. Beyond this research, Frédéric is a very, very good teacher. He's responsible for mathematics and physics teaching at the Chimie ParisTech and lectures on surface physics not only in France, but in Spain, the University of Cadiz, and also in University in China. And for several years you did this at the Sun Yat-sen University. So please join me in welcoming Frédéric, please.
So, in fact, the heat in Paris is for the moment higher than here. So this is in fact to have some fresh air that I came to Rome. So thank you very much for the introduction. Good morning, everybody, and thank you for being here. So first, I would like to thank you for the opportunity to be able to show you some of my results on the role of surface heterogeneities on reactivity. And first, I will briefly introduce the group of physical chemistry of surfaces. tell you which kind of topics we are studying, the methodology that we are following, and the platform that we use. And then in the second time, I will show you what kind of topics we are studying with an example on the initial stages of reaction of stainless steel. So after presenting you briefly the context, I will show you that the chemical and structural heterogeneities that you can find on the surface are in fact controlling the reactivity of the material. And in fact, we can see that some heterogeneities are self-organizing, and they have a very large influence on the reactivity of the material. And in fact, the reaction mechanism are depending essentially of these heterogeneities. Also, the chemical and physical properties of the layer of oxide that we can grow are depending on these initial heterogeneities. And then after this, I will briefly tell you some of the project we want to develop in our. So we are a relatively small group, so the group of Physico-Chimie des Surfaces. We have 10 permanent members, presently 15 PhD students and 4 postdocs. And we are part of the Institut de Recherche de Chimie Paris, which is one of the labs of Chimie ParisTech, which is the School of Chemistry of PSL University. So we are located right in the center of Paris, in the 5th district, so close to Marie Curie lab, close to the Panthéon, to Jardin du Luxembourg. So it's a relatively nice place. The problem is more related with the fact that we are in a 130-year-old building, which, as you can see, is sometimes a problem for the space, and also a problem of the building, which is slightly too old to do sometimes the modern sites. But okay, there are advantages and disadvantages of being in the center of Paris. So the topics that we are studying are essentially related with metals and the reactivity of metals and their oxide. We are covering a quite large range of different environments, from aqueous environment to ultra-high vacuum. And we are studying different topics such as electrochemistry in aqueous corrosion, biointerfaces, biocorrosion, biomedical application, also surface treatments of surface to modify the reactivity with, for example, coatings, organic inhibitors, like in the case of mercaptobenzothiazole, which is an inhibitor of corrosion on copper, here studied by scanning tuning microscopy. Also self-organized structures like nanostructure oxide film and structure rows of oxide that are grown on copper, and also some other alloys like binary alloys like stains. And so I'm involved in the 2 last topics, and I lead the surface reactivity at the nanometric and atomic scale. So our approach to study the reactivity is quite different from the classical approach, which is generally based on a large number of measurements in condition close to real one. With the problem is essentially related with the difficulty to control all the parameters that you have in real condition, and makes things more difficult to extract some fundamental behavior. So our approach is Surface Science 1, where we'll have much less experiment, but we will try to work in highly controlled environment in order to try to understand the very fundamental mechanism of reaction on these optimized and simplified model structure. And the idea is to identify the mechanism of reactivity at the atomic scale and to see what are the parameters that are influencing. And in fact, we can see that the heterogeneities that you have at the surface is really important and essential to understand this reactivity. And this is the reason why we study the very initial stages in a very controlled environment to try to understand this mechanism. So the techniques that we are using, here I will just present the ultra high vacuum techniques that we are using. So I will show you 4 different systems. The first one is just a photoemission spectroscopy system, which is the commercial one, where we have 6 channeltron and a resolution, imaging resolution of better than 20 micrometer. We have also connected to this preparation chamber, sputtering, annealing, growth facilities, and electron diffraction. And connected to this, we have, like on every of our system, we have a glove box where we can transfer the sample directly from ultra vacuum to this glove box to do some electrochemical treatments and some electrochemistry measurement, and then go back to the UH. The second equipment is a time of flight secondary ion mass spectrometer, where we have an analysis chamber with a primary gun of bismuth and sputtering gun for depth profiling of cesium, time of flight analysis. Again, we have a glove box for electrochemical treatments and a preparation chamber with sputtering and annealing as usual. And we have different mode of measurement for these stuff teams. We can do surface spectroscopy in order to have an idea of the elements and the molecules that are present at the surface. We can also do surface imaging, so to have a chemical mapping of the surface. We can do some depth profiling. So with the cesium gun, we can sputter and analyze with the bismuth gun, and then have information on in depth of the evolution of the composition of the material, which is important when we are growing layer and when we are doing some reactivity. And then we can combine the surface imaging and the depth profiling to have a 3D chemical mapping of the structure and identify some specific, yes, I forgot to mention that the resolution, lateral resolution that we have is limited to a few hundred of nanometer, but it's generally enough to see some corrosion effects. So the last 2 equipment I will present you are the one I'm in charge. So the first one is a STM1 Omicron, one of the first systems sold by Omicron. In fact, I think is the first one. So this is a STM at room temperature with, again, some preparation chamber for preparation, growth with Auger and lead measurements. Then we have a reaction chamber where we can expose the sample to gases from 10 to -9 to atmospheric pressure, from room temperature to 900 degrees Celsius to grow some layer on the surface. And we can also do the same, obviously at lower pressure, but we can also do the exposure while we are doing the scanning tunneling microscopy measurement. So we can follow in real time the reaction at the surface at room temperature, but at least in a range that enables us to follow this. Then the last platform, which is also the last one that arrived in the lab, is a platform where we have different techniques of characterization. There are three main chambers. One, which is the preparation chamber, so again for preparation, growth, and electron diffraction, which is also connected to atmospheric pressure cell, where we can go up to atmospheric pressure at 900 degrees for some high temperature treatment. And again, a glove box connected for electrochemical measurement. And then in the second main change, the first analysis chamber, we have an Institut XPS where we can expose while we are doing the measurement up to a pressure of 10 minus 4 millibar, thanks to differentially pumped reaction cell. And also at temperature varying from room temperature to 900 degrees Celsius. We have the ability to work with snapshot mode, which is in fact recording the 128 parallel channel at the same time. So we can do one spectrum at one shot with 128 points. And if we want to have a good statistics, we can record for generally about 10 seconds, and we can follow while we are exposing to the reactive gas, for example. While we are exposing, we can follow the reaction at the surface. I will show you some examples of this. Connected on the same preparation chamber, we have also an Institut STM where we can also do the exposure up to minus 6 millibar, and we can obtain atomic resolution up to 700 degrees Celsius. So while again we are doing reaction at the surface. So to now turn on the different kind of topics that we can study. One of our big topics, as I said, we are interested in reactivity of metals. So in this context, metal corrosion is a really major societal problem from the point of view of safety, performance, and productivity, but also from a financial cost. It has been estimated that in industrialized country, the cost of corrosion is roughly 3% of the gross domestic product. So really important from this. So obviously, we are not studying the structure when they are in this state of corrosion, but you can see that this is really something that can be a problem for the safety. This is a bridge in China that is a state, but what you can see is that in fact the corrosion is generally starting by pitting corrosion, so very localized problem. And the idea is to understand all heterogeneities at the surface can be responsible for this starting of the corrosion, because if we can stop this initiation, then we can prevent and reduce significantly the corrosion of this system. So in this context, stainless steel is a very important industrial material that is used in really many applications in various domains, from surgical tools to cutlery to automotive, electronics, biomedical, also in the oil industry, also nuclear power plant. So many applications for stainless steel, but as I told you, although we are interested in this industrial material, we want to apply surface science techniques. And so we are working with some model crystals, so single crystal of this model austenitic steel of 304 and 316, which are very used stainless steels, with samples which are in fact single crystal of iron, chromium, nickel, and iron, chromium, nickel, molybdenum for the two 304 and 316 alloy on single crystal oriented with the 100 direction. This is a FCC structure in this concentration. If we want to understand how stainless steel is protected from corrosion, we should know that, in fact, very fast, there is a nanometric chromium oxide layer, which is formed at the surface. This is generally corrosionists are explaining the quality of resistance of corrosion to stainless steel. But in fact, this view is clearly too simple, because we can see that if we are looking at the surface and the oxide layer, there are many heterogeneities which are changing this very simple view. And we need to understand what's happening at the atomic scale, really to understand how we differ from this real, from this very simple model. And so the first heterogeneity that we have to consider, which is generally forgot by many corrosionists, is that the surface do not have the same composition of the bulk. And for example, if we are looking at the surface of this material, so this is the 316 material with in the bulk 17% of chromium. If, for example, you are polishing and sputtering your surface, you can see that you have at the beginning a depletion of the chromium. So this is a spectrum. So this is a recording of the chromium 2p signal, which has been recorded in the snapshot mode I explained you. So we are measuring the full spectrum of chromium while we are increasing the temperature. And you can see that after 300 degrees Celsius, there is a first increase in the amount of chromium at the surface. Then after 600 degrees, you can see that the chromium is still increasing, and you can see that we can go from 13 to 32% of chromium. So really a change in the surface composition, which is quite significant. We can also see some nitrogen, which is in fact only present under the form of traces in the bulk, but which can be significantly present at the surface due to annealing. And so there is a co-segregation of the chromium and the nitrogen at the surface after 600 degrees Celsius. So the first heterogeneity is, as I said, related to chemistry, but in fact the composition of the surface is even more complicated than this, because if we repeat a cycle of sputtering and annealing, then we will have a change in the composition. And so it will also depend on the history of the preparation of your surface. So in fact, you will almost never have 2 times the same composition and the same structure of the surface. So it's really complicated to say that we have one composition. Here, for example, you can see that if you increase the number of sputtering and annealing cycles, then you will have a depletion of the chromium and the nitrogen at the surface, which is following the same tendency with the number of cycles. And again, the composition is never the one corresponding to the bulk material. So this heterogeneity of composition, we will see, will have a large influence on the reactivity of the material. If now we are looking at the structure of the surface, so for example, here the structure of the 304 surface, we can see on this surface that we have, and on this profile, that we have some alternating atomically flat terraces of about 10 to 20 nanometer, which are alternating with some steps of 3 to 6 atomic planes, okay, here. And if we are looking at what's happening on the terraces, we can see that we have some vacancy lines, which are periodic, with a periodicity of about 5.6 nanometer, with a depth of about 20 picometer in height on these surfaces. If we want to look more clearly on what's happening on the terraces, I leveled out all the planes just to show you here. So this is the same image where I just leveled out all the planes just to see better the contrast on the terraces. And you can see that we can clearly see now the atomic resolution at the surface. So each dot is corresponding to one atom at the surface. You can see also some chemical contrast because we have iron, chromium, and nickel at the surface. So they will give some chemical contrast, some different intensity in the STM image, and we can also clearly see now the vacancy lines, which is much deeper than the corrugation at the surface. If we look now at the homogeneity of the composition, you can see that in fact we have, as we have said, we have different heterogeneities of chemical nature. In fact, we can also see that at some place on the surface, typically at the top and the bottom of the step edge, we have a change in contrast, which is associated with a change in the chemical nature of the surface, and which is in fact corresponding to the region, the area of chromium nitride accumulation. If we are calculating the amount of chromium nitride that we have at this position, this is consistent with the amount that we see by spectroscopy measurement. On the terraces, we have a surface which is reconstructed, which is root by 2 rotated by 45-degree reconstructed. We can see here the profile, the atomic resolution, and you can also see some change in the 8, which are larger than the atomic variation, which are in fact related to electronic effect at larger distance on the surface. If we are now focusing and try to understand why we have these vacancy lines, you can see that in fact the width of these vacancy lines is, if we go from this atom to this atom, this is 3 lattice parameter, which in fact correspond to 2 missing rows of atoms. So the model we can make this, you can see that we have, so the root 2 reconstruction here, this is the 1 by 1, and you can see the rows of atoms, so from the top, and here from the side view, this is a profile, STM profile, where we can see that we have these 2 missing rows here. And as I said, this vacancy lines, so these 2 missing rows, are periodically aligned, which may seem strange that we have some periodicity, but in fact, this self-organization is quite common. In fact, if you look here, this is not when I came to Rome, this is when I went my last trip to Denmark. Probably I could also have taken the same picture here, but I was in the 8th seat, so I was not able to see the clouds. But you can see here, for example, the line of clouds which are self-organizing. So there are many things which are self-organizing. There is a poster there on the clouds and the rings of Saturn, which is also a self-organized system. And we can understand why we have self-organization, which in this case is slightly different than self-organization of clouds, but here the self-organization is due to the surface stress that is created when a surface is created. So if you imagine, for example, that we have a metal with an homogeneous electron density and the positive ions, you imagine that it's infinite in any direction, and we cut the sample into 2 to create a surface, then there will be a rearrangement of the electron at the surface that will increase the, in the case of a metal, that will increase the interaction between the atoms. And so it will change the equilibrium distance, it will change the lattice parameter at the surface. And this can be modeled very easily by very simple model, which is the Frankel-Kontorova model, where we imagine that the atom at the surface can be represented by some interacting atom, some force constant here, and interacting with the bulk, which is corresponding to some periodic potential. And the distance, the equilibrium distance of the surface atom is different from that of the bulk. In fact, if the forces are high enough, then we can have, it can be enough to break some bonds at the surface. And if the bonds are broken, then we have some point force which are appearing at these atoms which are not anymore linked together. And if we calculate the elastic energy associated with this point force and the displacement of the atom from their natural position, then we can calculate the elastic energy, the surface elastic energy of our system. If we are calculating this, if, for example, we are assuming the linear elastic model, so that for point force, we would imagine that the displacement of the atom will decrease as 1 over x. And obviously, this will depend on the elastic constant of the material. Then if we integrate this, we can define some force field. So, the force field, as I told you, we will have some force at every atom that is not linked. So every side atom of the vacancy, we will have positive force. This point force, so we can simulate them by Dirac distribution. And so we have the positive force here, 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 and we have the negative force at this position. If we calculate the displacement, which is just the convolution of this force field with the displacement for one point force, then we can calculate the elastic, which is the integral of the sum of the inverse, which will give you the sum of logarithms, so which will give you the logarithm of a product, and this product can be simplified and give you some function like this. So this will be, this elastic energy will depend on the periodicity of your system. And if we want to calculate the total energy, then we also need to take into account the fact that to create a vacancy, that we need to break some bonds, so it costs some energy. And so the total energy will be, in fact, the energy needed to create this bond per unit area. So this is linear energy. And here, this is the energy that is gained, let's say, by the reduction of the elastic energy. If we are drawing this, you can see that we have a potential like this, where we have a minimum value, which in our case is corresponding to 5.6 nanometers, with a distance d, which is, as we have said, 3 times the lattice parameter. And so we can understand that it should be periodic. In fact, if we are looking at the experimental data, and if we are drawing the theoretical shape of the distribution, the theoretical shape of the distribution centered at 5.6 nanometer is the red one. And you have here the histogram of the measured distance, so measured several hundreds of period on the surface. And you can see that we have, in fact, a two-mode system where we have a second mode, which is at about double distance of the first one. In fact, this is really due to the fact that there are different mechanisms of relaxation. The first one being the vacancies, another one being, in fact, a change in the composition, local composition, and also sometimes you can have a relaxation of the stress, which is not made by changing the structure, but by changing the composition at some place. And this is the reason why we have these two modal distribution of vacancies. So now let's turn that we know what we have on the surface. Let's turn out to the reactivity of this surface. So for this, we exposed the surface to oxygen. As I told you, with the snapshot mode, we can take one spectrum every 20 seconds. So we recorded for 5,000 seconds. So 500 spectrum were recorded while we were exposing to oxygen. So you have the pressure as a function of the time on the same scale. You can see that for very low pressure, we already have some oxidation. If we increase the pressure, we can speed up the oxidation of the surface. In fact, I can show you how it looks like. So here we are measuring the oxygen 1s as a function of the pressure, and here you have the exposure in Langmuir. And this is the spectrum. We have one spectrum which is measured every 10 seconds. So we can integrate the area of the oxygen 1s to draw the kinetic of oxidation of the material. And you can see that this is quite fast. In a few Langmuir, you already have some kind of saturation. Few Langmuir is corresponding roughly to a few nanoseconds at atmospheric pressure. So that means that this nanometric oxide layer is formed quite fast. Here you see that at 15 Langmuir, we already, so in the case of stainless steel at 250 degrees Celsius, we have already almost saturated the reaction at the surface. So if we now look at what's happening as a function of the composition, I told you that depending on the preparation, we may have some different composition. You can see that if we are comparing material, so surface with high chromium density or lower chromium density, so we will have behavior to oxidation which will be completely different. So the reactivity speed is different, but also the composition of the oxide is different. Obviously, the one with the higher chromium content will have an oxide with a higher chromium content, which is what we could expect. But we can also see that below this oxide, the composition of the sub-oxide layer is different again from the bulk, but almost similar, not depending on the initial chromium content. And so, once again, these heterogeneity at the surface are really completely changing the properties of the oxide which is formed. If we are looking now more deeply at the analysis of the photoemission spectra, we can, at different exposure, look at the composition of the surface. We can identify, in the case of iron, two different oxidation states, the 2+ and the +2 and +3 oxidation state of the iron. And we can also identify the +3 oxidation state of the chromium. And as we have said, there is some chromium nitride at the surface. If we are looking at the evolution of as a function of the exposure, we can see that in the case of chromium, we have a very fast decrease of the metal component, which is associated with the growth of the oxide, which is also very fast. You see that in a few Langmuir, we have already a very high amount of chromium oxide, which is what we want to, because this is the chromium oxide which is passivating the material. So we hope that we will have a fast increasing chromium oxide layer. But you can also see that after some time, the chromium intensity is decreasing. In fact, this is due to the fact that some iron oxide is growing on top and attenuate the signal of the chromium oxide. And there is a competitive growth with iron oxide, which starts slowly, but in fact continues for quite a long time. And so we have initial preferential formation of iron 3+ oxide, but it will continue above the chromium oxide. If we are calculating the thickness of this chromium oxide and iron oxide, we can see that in fact the chromium oxide is increasing very fast. In a few Langmuir, you already have 1 nanometer thick chromium oxide. The iron oxide is increasing much slowly, but it will continue for a much longer time, while the chromium oxide is saturating very rapidly. So if we now look at the structural evolution as a function of exposure for the very beginning of oxidation. So this is about 1 Langmuir, so the equivalent, say, of 1 nanosecond at atmospheric pressure. We have a change which is limited to the step edges. So if we are looking, you have here some islands which are formed, some nanometric islands, about 2 nanometer square islands, which are formed at the step edges, which are in fact chromium oxide, because as we have the 2 techniques in the same platform, then we can do on the very same surface, we can do the chemical and the structural characterization. Here in photoemission, we just have chromium oxide, so we know that what is appearing is only chromium oxide. So once again, I have leveled out the plane just to see what we have on the terraces, and you can see the atomic resolution on the terraces, where now we have the surface, the place where there was the chromium nitride, which is now completely modified with the formation of chromium oxide. We have also some defects which are appearing, which are in fact chromium atoms which are extracted from the terraces and which are, we think, bring by these vacancy lines to this area on the step edges where they are more reactive. We have sometimes some modification and formation of defects and vacancies of chromium on the terraces, but most of the reaction is still continuing at the step edge, which are generally more reactive side. So if we are now continuing to up to 3 Langmuir, then we can see that the step edges are now saturated, and we start to have some formation of islands which have the same dimension, same orientation that the step edges. So we assume that they are chromium oxide islands, which are formed on the terraces also. And you can see that now we have completely lost the route to reconstruction. So all the chromium at the surface has been used for creating chromium oxide. And we can also see that these islands are organized. So they are self-organized for the same reason that I showed you on the surface. This is again related with the surface stress, because here, for example, if you are absorbing some oxide, let's say, on your metal surface, then you will have an electronic redistribution, so you will change the force. If you change the force, then you will have some point force that will appear. If you increase the force, and the force, the interaction, then the force will be this side. If you decrease the interaction between the metallic atoms, then the force will be opposite. But this is for the same reason that we will have this self-organization of the islands at the surface. We can also see other structures which are appearing on the surface, which are also at reactive site on the step edges, which can be identified to iron oxide. And this is confirmed by the fact that this is the exposure for which we have the appearance of iron oxide in the photoemission spectroscopy measurement. And so we know that what is appearing at this stage is in fact iron oxide. And so we have iron oxide, which is appearing very fast also at the very beginning, before the chromium oxide is finished, which is a problem for the resistance to corrosion of the system, because the idea is that the chromium oxide should be protecting the surface from corrosion. So if we summarize what we have seen till now, at the beginning, we have a reconstructed surface with some modified step edges. And so we have a composition which is different, which is reconstructed. We have here some change in fixation. Then we have very rapid oxidation of the step edges and some vacancies which are created that can diffuse to the step edges using the transport along the vacancy lines. And then we have the formation of the nucleation of chromium oxide on the terraces. So that means that we already have consumed all the chromium from the top surface, and also the appearance of some iron oxide. If we continue the exposure, then we have another structure, hexagonal structure of chromium oxide, which is appearing on the surface, which is now covering the whole surface, but we already have the iron oxide at the step edge, which will continue to grow. And so if we are now going up to larger value of 100 Langmuir, then we have the surface which is fully covered with the chromium oxide, but we still have some iron oxide which is growing on top with different orientation. With some orientation, for example, Fe3O4, the 001 surface is growing much faster than the 111 orientation. So you can see in the STM image that the 8 is much higher, it's much brighter island. So this orientation is growing faster on the surface. So not all the orientation of iron, there are several orientations, but not all are growing at the same place. So if we are continuing to about the saturation, we can see here that the surface is fully covered with the chromium oxide, but with some dots of iron oxide, and iron oxide which is forming on top of the surface. If we are looking at the structure of the surface that we can identify mainly iron oxide, the chromium oxide being below the iron oxide. So if we summarize, that means that So we have initially this iron oxide that starts at the very beginning, that is growing fast, and also at some point when the chromium oxide layer is almost completely finished, then we have the diffusion of iron through this unpassivated area, where we can have some growth of oxide on top of the chromium oxide. And so the problem is that in this case, this pillar of chromium oxide is really the weak points where we can have some pitting, because there is no protection with the chromium oxide, and so the corrosion can penetrate from this point, and then once it's reached the material below, then it progresses, and this pitting pits will grow under the chromium oxide layer, which is passivating some place, but not all the plates. And so the idea is to try to see how we can improve. So if we conclude that I showed you that the surface is much more complex than what most of the corrosionists think it is. In fact, the surface is reconstructed. There are many heterogeneities, although it's an ideal surface, let's say, the single crystal surface. There are many heterogeneities. So obviously, you can imagine on the real surface that we have much more defects and much more heterogeneities that should be taken into account if you want to understand the corrosion mechanism. And we have seen also that there is some preferential nucleation, atomic transport, which are each favored by these heterogeneity at the surface. So clearly it is not possible to understand the initial reaction on the surface if you are not taking into account this very important heterogeneities, composition and structure at the surface. So the idea is to find out how we can improve this. So here, this is a very fundamental study in oxygen. Obviously, the chromium oxide is not formed in oxygen, in pure oxygen, but in atmospheric conditions. So there are also some interaction with other molecules, for example, with H2O. So we are also studying the influence of other oxidizing agents in different conditions, just to see if we can improve the quality of the passivating layer. Okay, so as I said, I will just finish by briefly introducing you some project that we want to develop, which is associated with high entropy alloys. In fact, many people are interested in high entropy alloys. Alloying is, the art of our study. It has been used for 1,000 years to improve the property of the metals with the work of binary. And here I showed you stainless steel, which is a ternary alloy, and even a quaternary alloy in the case of the 316. But all these alloys are made of one principal element, which means that in the case of stainless steel, we have mainly iron, and then you add some other elements just to improve the quality of the material. The idea of high entropy alloy is to have multi-principal element alloy. So to have different elements with almost equimolar composition in the idea of having improved properties. The first, let's say, high entropy alloy that has been realized has been made by Cantor in 2004. This is the iron, chromium, nickel, cobalt, manganese. The idea is that of this high entropy alloy, which gives the name to the alloy, is that we can stabilize the structure of the system by improving the mixing entropy. So the mixing entropy will depend, obviously, on the relative concentration. And so if you increase, and if you have an equimolar composition, then you will increase the entropy. For example, if you imagine that you have 5 elements at 20% each, then the mixing entropy will be equal to log of 5, which is 1.6. And so relatively high entropy, which means that you can stabilize the total energy of your mixing by adding a large number of atoms. It has, as I said, since the discovery, used by many people, but most people are interested in the mechanical properties. And a few people are interested in the surface properties, so the reactivity of this material. And in fact, we can see that they are very promising for surface reactivity, but very few people are studying. For example, I think that there is only one STM paper on high entropy alloy single crystal that has been. And so the idea is that if we want to apply our surface analysis, surface science methodology to this, we need to have good quality and very good quality surfaces, which for the moment is not really the case. And the idea is to create some nanofilms of nano thick films of high entropy alloy, starting, so you've seen that the contour alloy is iron, chromium, nickel, cobalt, and manganese. So if we start from stainless steel, and we could imagine that we can add some atoms at the surface, we can deposit some selected metal at the surface, we can characterize, we can, by annealing, produce some surface alloy and characterize all of them. Obviously, this is a very simple scheme. In reality, it will be much more difficult to obtain this alloy, but in fact, we already have preliminary results that show that we can manage to form some surface alloy by depositing some element at the surface. And so the idea is that we can study the reactivity of pure metals. So this is the reactivity to oxygen of different pure metal composing the high entropy alloys, iron, chromium, cobalt, nickel, molybdenum. And you can see that we have studied 2 specific with slightly different composition high entropy alloy. And you can see, for example, that with this one, we have a reactivity which is much higher. So the idea is that we have some synergetic effect that makes the reactivity of the high entropy alloy larger than the reactivity of all of the others, which obviously would be interesting for catalysts, for example. This is also called the cocktail effects, that the cocktail is better than every component. And so the idea is to continue to work on this. We have already made some preliminary results to see the ability to use this high entropy alloy for CO2 reduction, for H2O in electrocatalytic dissociation. And the idea is, as I said, to grow this nanofilm, to study them with STM, with photoemission, in order to be able to see if we can tune the surface composition to favor some reactivity at the surface. So I think I will finish this. I already take a lot of time, so I will just finish by thanking the PCS group member, especially the students that take part to this work, and you for your attention. I should also mention that it has been funded by an ERC advanced grant and the Région Île-de-France.
Thank you very much, Frédéric. Maybe anyone of you curiosities wants to make a questions, or please, Fabian.
Okay, we were discussing about the single crystals of the stainless steel. Are these easy to, because we never saw companies selling those.
In fact, some results I showed you are samples that we had from very long time, which have been produced by scientific lab, but the new sample that we have, the 316, for example, is produced by a company which is Matec. So they are obviously it cost quite a lot because they are growing the rod just for us. So we can buy 10 samples the same price as we buy one. So they grow the rod for us, and after the cut.
And did you ask for a miscut in order to have those?
No, in fact, the one which has the it's about 3-degree miscut is the one that has been produced by the lab in Mines.
And another question, sorry.
The other one was aligned at 0.1 degree.
Before sputter annealing, I guess the surface contains chromium, iron, whatever. But after sputter annealing, it's almost only chromium, as far as I understood.
The surface is polished. It's electrochemically polished and introduced, and we sputtered. So we have iron, chromium, nickel at the surface in composition which are different from that of the bulk, but we have a mixture. And then we anneal, and then we see that we have some diffusion. In fact, from a thermodynamical point of view, if the chromium could diffuse, or we should have a pure chromium surface. But the problem is that we should have a pure chromium surface at low temperature. And obviously at low temperature, the chromium cannot diffuse to the surface. And if you increase the temperature, then you should tend to a composition which is the one of the bulk. But while you are eating, then you let the chromium diffuse to the surface. And so this is a competition between how fast you eat, how fast you cool, just to have this composition. If we were working at high temperature, then we should have the same composition at the surface than in the bulk. But when you cool down, then the chromium should increase. But when you cool down, there is less diffusion, and so it's really difficult to have one composition.
But
why should the chromium go to the surface? Why should chromium go to the surface at low temperature?
Because its surface energy is at low temperature. So at 0 Kelvin, from a thermodynamical point of view, as the surface energy of chromium is lower than the surface energy of the other element, from a thermodynamical point of view, there should be only chromium to minimize the surface energy. So the problem is that there is no diffusion.
And the bulk energy with temperature.
Sorry?
There is a crossing of the surface energy and the bulk energy It is not true that the surface energy is lower at a high temperature. Only
here, but if you look at, imagine that you have a graph of the composition as a function of the temperature, then chromium should be equal to 1 at low temperature, and then it will decrease like this with the temperature, and you should have. But the problem again is that it's not only thermodynamics. It's thermodynamics and kinetics. And so the competition between the kinetics of diffusion and the thermodynamics is making that you have almost any composition. In fact, my PhD student just wrote a chapter which was called the ever-changing surface, because he prepared hundreds of surfaces and never had exactly the same composition.
Okay, but sorry, just one last thing.
Yeah,
The atoms that you have after spatter annealing on the surface, that you get the root 2 by your 2, these are
This is after
chromium.
annealing.
These are, you said that these are chromium, or it can be chromium, iron.
After annealing, so before annealing, we have iron, chromium, nickel. To have the reconstruction, we obviously need to anneal, and then we have iron, chromium, and nickel. Maybe if we are looking at the surface here after preparation. Here we have chromium. We have chromium, iron, and nickel at the surface. So with a composition,
It's not only chromium.
no. But when you have when you are exposing to oxygen, the only vacancies that we are creating are chromium vacancies. But yes, it's a mixture. This is what we can see on this away. On this image, the contrast that you can see is really due to the fact that we have iron, chromium, and nickel at the surface. So these are this contrast here is due to the fact that we have different elements at the surface. On this surface, we should have something like 12% of chromium, 9% of nickel, something like that. Which is less chromium and nickel, and we have also nitrogen here. So this is less chromium and nickel than in the bulk, but we still have the different at the surface.
Other questions, maybe curiosities? I have one, but just general one. So there are ERC programs to finance this kind of studies.
Yes.
Are there a lot of projects, or this is only, a small?
This is only a
project.
part of a larger project. There was also in the project, there was also some electrochemistry study of the corrosion. Maybe if it would have been only surface science oriented, maybe we would not have the ERC.
Okay. So surface science is hidden in a
This
very
is
large
one
project,
of
no?
the three
more than
main
for the
team
other.
of the ERC.
Okay. So please answer.
No, just a curiosity. I mean, not an expert. So you wanna, as far as I understood, you create a native chromium oxide layer. So if you put chromium oxide from the very beginning, like ALD, for example, what's up? So you can really cover it without problems.
Yes, I mean this is something which is used for long in the industry. You just have not even a stainless steel, just normal steel, and then you deposit chromium on top of it. So this is a way just to avoid corrosion. The problem is almost the same, that slightly different than having stainless steel, because with stainless steel, if you scratch the surface, then you still have chromium in the bulk, and so you will reform some chromium oxide. If it's just a deposit and you have a scratch in your chromated bumper on your car, for example, before it was like this, they just had steel, normal steel, and they deposit chromium. And then if you have a scratch, then it will corrode, or sometimes it can even corrode below the chromium layer, and then you see that the chromium is just peel off the chromium. So yes, there are possibilities. These are more other solution to corrosion, which is inhibition of the surface. The problem with this inhibitor of corrosion is that when you remove them, then you still have corrosion. Why in the case of stainless steel, if you remove the oxide layer, then you will reform the oxide layer.
So what the question was, I mean, you showed that, I mean, nevertheless, you have chromium oxide. I mean, you still form these pillars of iron oxide. So when you put from the very beginning the chromium oxide, then you can form these pillars or not?
It depends probably of the if you are depositing directly chromium oxide on the surface, it's probably will be the same kind of problem of heterogeneity at the surface.
You change the mechanical properties.
Also.
But I'm interested about the high entropy alloy. So they are given in powder or layer?
Sorry?
In powder, they are powder sample.
No, it's
You grow. But
no,
generally,
the preliminary result I showed are single crystal of high entropy alloy.
ah, okay.
So you can obtain some single crystal. We try to have some good quality surfaces. It's difficult, for example, with the control alloy, it's difficult to have a good surface quality keeping the high entropy character. For example, you need to organize your surface to anneal, and the manganese will leave the surface. So the condition in which you can obtain a surface which has the right structure, you will have only 4 elements, which is not really any more high entropy alloy. So this is the idea that what we have done is that we have deposited other elements on the high entropy alloy and formed some surface alloy to regain this high entropy character at the surface. So for example, on the counter element, we have deposited manganese and platinum so that we have 6 elements at the surface from this alloy.
But my question is also, there is a dishomogeneity on the surface of this, the composition of these elements. So if you move different parts, you can find different composition?
No, this is the idea. In fact, what we have seen is that it's a real single phase system. So, which is,
you mean that?
This is the reason why,
that,
this is because of the high entropy alloy that we can have the stabilization of this single system. On classical alloy, you have generally intermetallic particles where you have different phases with different composition on the surface, which are not stabilized because of the lower entropy. The idea is that in the case of high entropy alloy, we can have only one single phase with one single composition and structure. This is at least what we observed on the alloy that we have studied.
Thank you.
No questions even from the web. So I think we can thank Frédéric. Frédéric will be here next week.
Right.
So if you want to talk with him or just have a curiosity and then to be satisfied, then you can ask him.
Fred, I saw the Davide Cerati.
Yeah.